How's it going, everybody? We are the Dominance Landmine team sponsored by Lockheed Martin. We are all senior computer and electrical engineering students at the University of Central Florida, and our team is composed of Corey Hogue, an electrical engineer, Joe Rivera, an electrical engineer, Kristopher Sipe, a computer engineer, and Justin Wu, a computer engineer. Our customer, Lockheed Martin, requires a stationary mine capable of target identification, target tracking, a wireless video data link, and autonomous disruption to successfully disable an unmanned aerial vehicle using our custom-designed net launcher. Some of the customer requirements defined by Lockheed Martin include dimension size being limited to 1.5 feet cubed, a blast radius of 3 feet by 10 feet high, staying within a budget of $1,050, as well as including safety features such as an e-stop and a wireless video data link to transmit video data from our stationary landmine to a land station nearby. Some of the other necessary requirements to include in our design is a bounding and metadata box that will show the confidence, the range of target, and the time of arrival of the drone towards our stationary landmine. To develop a stationary landmine, a custom chassis must be made to house all of our primary and necessary components to successfully disable a UAV. These components include our main computer vision hardware, as well as secondary hardware to control motors, as well as triggering our device. Shown in the following demo video is our chassis being powered by Group17 stepper motors. These motors allow for a panning and tilting motion to be achieved for proper tracking, targeting, and capturing using a custom net launcher. Our net launcher design has 4 major components: a CO2 adapter allowing for 12-gram cartridges which allow for easy reloading, brass piping for regulating the pressure from these 12-gram cartridges, a mechanical ball valve on our prototype launcher to release the pressure, which will be later traded out for an electronic solenoid, as well as a net deployment system to efficiently deploy our net around the UAV. In the following demo videos, we are utilizing the mechanical ball valve for initial prototyping. Once the net launcher prototyping was successful, it was time to integrate this net launcher onto the chassis while still allowing for a full range of motion to be achieved. Since none of the other components limited this range of motion, it was time to integrate further hardware into our design. Using our initial hardware integration block diagram, we incorporated a Jetson Nano for the computer vision, an Atmega chip for our secondary controller to control the stepper motors as well as triggering our solenoid, and provide power to all of our necessary subsystems. Shown first is the Jetson Nano and RealSense D415 depth sensing camera, as well as our USB device for our wireless data link. Moving on, this is integrated within our PCB design, our PCB providing power and a common ground, as well as our communication back and forth via UART. Next is our motor drivers, of which are also powered using our PCB. Signal is also routed to these motor drivers from the Atmega chip to allow the communication from the Nano to be translated into our mine movement. Also incorporated within our PCB is our triggering solenoid, which replaces our mechanical ball valve on our initial prototype. This solenoid allows for efficient triggering to disable a UAV autonomously. Moving on, our big easy motor drivers send the signals to the Group17 motors on the chassis. These motors allow for a full range of motion as shown before. Also shown is the bounding box where all these electrical components will be housed in the future. As stated before, electronic triggering is necessary for a full autonomous disruption. Replacing the ball valve with the electronic solenoid allows for this to be possible. Shown in the following video is a demo of our electronic solenoid triggering on and off via the Jetson Nano's input.
For the software libraries we'll be using, most of our programming will still be in Python for connecting the solenoid, motors, and external components to the GPIO pins on the Jetson Nano. OpenCV will still be used either through the Python or C++ APIs. TensorRT will be used if possible for hardware acceleration. However, cuDNN is a solid backup. We will be doing the majority of our computer vision programming in MATLAB using their deep learning toolbox to develop the neural networks, and then the GPU coder toolbox to deploy those networks and actually deploy entire functions, converting them to C, C++, and CUDA. We had created a custom dataset to train our object detection and classification networks. Currently, we have over 6,500 images of drones and 12,000 images of background. However, since we won't be competing at Lockheed Martin's Innovation Center anymore, we'll need to add more training examples of the drones that we do have on hand to test our device. The dataset is not very representative of any environment other than the Innovation Center itself. However, you'll see in our demo that the classification and detection is actually doing pretty well in certain environments. Our new plan is to create a new data set around a small drone that we have for testing purposes, and we'll continue to test on that small drone and hopefully get a good demo out of that. Here is an overview of our full computer vision algorithm written in MATLAB. We were able to utilize the RealSense SDK provided by Intel and some of their pre-made functions in MATLAB to pipe in information from our sensor. I'll show you where we're able to pipe in our depth image from this stereo camera right here. And we can also pipe in the color image as well. The main point of using MATLAB is to be able to create this MEX function to run our detector. So we can take a deep neural network and convert it to C, C++, and CUDA and target one of the deep learning libraries like TensorRT or cuDNN to accelerate that and make the whole process quicker. So here I'm just going through a quick overview. If we wanted to deploy this directly on the Jetson Nano, we can do this SSH client line up top, this through the Jetson function. We can configure it and deploy it as either an executable or a library, target specific deep learning libraries, and then do code gen really easily. We can also do deployment on the host itself, like what this example is. So we're able to generate this MEX function, right? And we also target the cuDNN library, do the code gen, and that's how we get the detector MEX function. So this function is a MATLAB executable, but it is written in C, C++, and CUDA using the cuDNN library, and it is much faster to run than just running the network through MATLAB's official functions. So I'll get it started here. Our GUI shows the frames per second, the difference between the bounding box and the center in both X and Y, and it creates it sends a -1 if there's no bounding box on the screen. So this will be used by the motors to move the center position of the camera to the center position of the bounding box that's being displayed. And only one bounding box will be displayed at a time. Right now we're demonstrating that we can show the red bounding box that Lockheed Martin requested, along with a confidence value and the distance to the target, which is computed from the depth frame. We also have this nice little e-stop button here, which exits out of the program and stops the pipes.
While significant progress has been made, there are still a few milestones that we need to reach before completion. Integrating all these subsystems into one is a big part of this project, of which has given us many issues that we are currently working through. Hopefully we'll have these resolved in the very near future and we'll be able to provide an awesome demo for everyone. This concludes our demo video, and we really hope that you enjoyed this. We can't wait to provide you with an awesome finished product at the end of the semester.